and gentlemen, we are recording. So, yesterday we spent a good amount of time talking about terminal velocity, and we talked about why terminal velocity happens, right? The fact that air resistance continuously increases. The fact that air resistance continuously increases to the point where it balances out the force of gravity acting on something, and the net force ends up being what? Zero. And then that also means if net force is zero, what else has to be zero? Acceleration is zero, and that means an object will then do what? Not speed up or slow down at all. Just continue doing what it's doing. And we said that the ultimate result of terminal velocity is an object that has zero acceleration. It's not standing still, it's just not changing what it's doing. And we said that was our first example of what concept? Yes, I guess, but we also refer to it as an object that is not speeding up or slowing down. Well, terminal velocity is a specific example of equilibrium, right? A situation where an object in equilibrium is subject to zero net force, right? It can't really be any easier than that, yes, right? Zero net force means that an object will not accelerate, right? They even highlighted it here. Notice, being in equilibrium doesn't necessarily mean that the object is at rest. So equilibrium can look one of two ways. An object that's at rest is in equilibrium, but also objects that are moving with constant velocity are in equilibrium as well. If we drew free body diagrams for an object at rest and for an object moving with constant velocity, regardless of if it's sideways or up or down or whatever, free body diagrams will look very similar to each other because net force has to be zero. Okay? Good there? All right. When we start talking about equilibrium, there's a couple forces that show up a little bit more often. The first force that shows up is a force that we call tension. Okay? Tension is just a fancy name for force that comes from a string. Oh, there it is. Tension is the force exerted by a string, rope, or wire that is pulled tightly. Okay? We don't treat it any differently than any other force. It's just a fancy name for a force from a string. So if we ask you to calculate the tension, or if we ask you to find the tension, that's just saying find the force. It shows up when we talk about equilibrium a lot of times because we can think of situations where something is suspended or something like this. Oh my goodness. See, I would have these props all ready if I didn't have to go to it. If I hang that hanger off of that string, granted it's still moving a little bit, but when it stops, right, those strings are keeping it in place. We hang it from the ceiling, or you hang a picture on the wall, or whatever it might be, right? Those are tension forces, but all it is a fancy name for friction, okay? Friction. It's a fancy name for force. In this sense, the string transmits a force from one location to another, right? Generally, if we think about, like, I don't know, a tug of war, okay? You pull on one end of the string, but your force ends up being exerted on the other end of the string, right? So we transfer that force from one place to another. That's kind of the thing, that's kind of the key about tension, right? It's just a force, but we're transferring that force from one side to the other side. Okay? Good there? All right. In your packet, you have this example right here. The picture should look familiar. It was on your test the other day, or at least one part of it was there. Okay? But it said, a person hoists a bucket of water from a well, holds a rope, keeping the bucket at rest, as in case 1. A short time later, the person ties the rope to the bucket's handle so that the rope holds the bucket in place, as in case 2. is the tension in the rope in case 2 greater than, less than, or equal to the tension in the rope in case 1? We said tension is just a fancy name for force. So let's draw some free body diagrams to examine what's going on. Okay? First, we'll do this as case 1. Okay? There's my bucket. Okay? Free body diagram. Notice this is a conceptual example. There are no numbers. So let's just go off what we know. All right. It says here, keeping the bucket at rest. We just learned that something at rest, what has to be true about it? Equilibrium, right? And that means that all the lines are the same length. Let's go put some terms in there, right? What is our actual definition of equilibrium?
The subject is zero net force.
No net force, right? And that means, Mohan, if we have more than one force, what has to be true about that? I guess I should go this. Can an object that only has one force be in equilibrium? No, right? If you only have one force, can the net force be 0? No. So we gotta have at least 2. Okay? All right. What's the first force that we should draw on this free body diagram? Let's go weight. Okay? I'm gonna change something here. Right? Haley, weight is just a fancy name for what? Nice, mass times gravity, or it's the force of gravity, right? So we add weight in here, and even though we don't have a mass, right, that's how we calculate the weight of an object, okay? That's always going to be acting on that object regardless, okay? But if it's in equilibrium, what else does there have to be? Up. How big? The same as the weight, right? In this case here, where is that force coming from? The rope, and that means that it's a what? It's a tension force, right? What? How many ropes are attached to the bucket in that picture, case number 1? Just one. So all the tension in that rope, right, or the tension in that rope has to be exactly equal to the gravitational force on the bucket. Good there? Okay. Now, let's go case 2. What color? Okay. Bucket, there it is. Okay. Case 2, the bucket is still in equilibrium as well. So we start drawing free body diagrams, right? First force we draw on our free body diagram is what? Weight. And the fact that we now changed it so that we tied the rope around to itself, does that change the green arrow? It's exactly the same as the green arrow in the previous picture. Okay? That what's happening around it doesn't change what gravity is doing to that bucket. But there is one other difference though, right? What's the difference between case 2 versus case 1? There's 2 tensions, right? Yeah, it's the same rope, but that same rope is pulling upward on that bucket 2 times. Does that make sense? All right? So, when we draw in those tensions, right, now we have 2 tensions. What has to be true about each of those tensions, or each of those forces? Okay, so that means this is actually weight over 2, right? In the first one, that tension is going to be equal to the weight. But here, each of these would have to be half the weight, right? Because together they have to add up, all right? Good there? So, the rope is going to feel heavier, the rope is going to feel like tighter in case 1 as opposed to case 2. No. It does add up, but there's it's coming from 2 different sources. Does that make sense? I see what you're saying. Because the one thing that's a little confusing with this is the fact that it is the same rope, but in two different parts. Okay, but Nate, because of the fact that it's like swinging around that pulley, right? It almost turns into like two ropes that way. That pulley has the ability to, I don't want to say like divert the force, but it changes the direction at which the rope is pulling, and so it acts almost like two forces. So in case two would be exactly the same as if like you were holding one rope and your friend was holding another rope, right? That would be easier for each of you if you were both holding the bucket as opposed to one of you only holding the bucket in case one. Ben, go ahead.
Would you also say it's greater because
Yeah, and that's the reason why that tension is greater, because there is only one force in case one, whereas there's two forces in case two, right? But in the end, though, Ben, the end result has to be what for the bucket? Yeah, it has to be equilibrium, right? We have to have a net force of 0. So the more forces we have in the upward direction, if we're holding that bucket still, we have to meet the condition of net force 0. Adding more adding more ropes doesn't necessarily add more force in the upward direction. It dilutes that force among the 3 ropes or the 4 ropes, because in the end, the total in the upward direction has to be 0. The total in the upward direction has to be the same as the gravity pulling in the downward direction, right? Now, if we put water in the bucket, what changes in these pictures? Everything. What changes first? The weight, right? So then the weight line would increase, and that would have to make the total in the upward direction increase. In case 1, that would make the tension increase. There's only one force. In case 2, it would make both of those tensions increase so that they balance out the weight. Does that make sense? There? Okay, let's try something a little different. Probably something you've seen before. Okay, it looks like this. So it says a 1.84 kilogram bag of clothespins. Does anybody actually have clothespins at their house anymore? I say your grandma, like that's. We don't really have clothespins. Like my mom has clothespins at her house, but we don't. We don't have a laundry line in the backyard, a drying line in the back of our yard. Actually, in the basement, yeah. Like my parents have one in the basement. So actually, the people that live behind me, there's like 2 streets that run back to back. So like my backyard neighbor, they have like a laundry line, and in the summertime they have like their sheets out there and everything like that. So it's very old timey. So All right, so it says here, a 1.84 kilogram bag of clothespins hangs in the middle of a clothesline, causing it to sag by an angle of 3.50 degrees. Find the tension T in each part of the clothesline. So, they have pretty much drawn our free body diagram for us here, right? They've added 3 forces that are acting on this acting on the bag of clothespins, right? We've got the weight force here, okay? And then we've got tension this way, and then we've got tension this way, right? Actually, I'm going to do this. I'm going to make this one pink. Oh. So it's a little different than the red that's on the picture, okay? All right. We can tell a couple of things. Actually, let's go through the process, right? So, what are we trying to figure out here in this problem? What is this question asking us to do? Pink tension. Tension. So it's kind of like a sh sound, even. It's an ION. Where is it? It's an ION, so it gives you like the, tension. So. All right. Pink tension, blue tension. Okay? Things they gave us to work with. We can kind of skip some steps here. So what's the first thing they gave us to work with? Or actually, really, there's 2 things they gave us to work with. What's the first thing they gave us to work with? They give us the mass, right? 1.84 kilograms. But we can right away turn that mass into a what? Into a weight, right? So the weight is equal to m times g, right? Anybody got the calculator out? Right. And because weight is a force, that's in newtons, right? Okay. Weight is a force. It's the force of gravity. Okay. Then they also gave us this angle theta and this angle theta, right? I'm not going to write them in right now because I don't want my drawing to get too complex, right? But it told us that the angles theta are 3.5, okay? And then there's one important piece of information that they didn't exactly give us, but is true about this bag of clothespins as long as the wind isn't blowing, right? If that bag of clothespins is just hanging there stationary, like the hook on the string over there, what has to be true about that bag of clothespins? Let's go more generally. What would we say about this bag of, it's in equilibrium, right? So, if something is in equilibrium, right, that means that net force has to equal 0, right? Even though it didn't specifically say that bag of clothespins is in equilibrium, it has to be true. It's not moving. All right, let's talk about how we handle this. First, our green force is up and down, but blue and pink are at an angle, right? We've talked about, over the past couple weeks, how we handle forces that are at an angle, right? We can do SOHCAHTOA to get what? To get the sides. Do you remember what the name of those sides are? Fuad, do you remember the name of the sides? We talked about it yesterday. What do we call the sides of the triangles? Well, that's what we call them in math class. We give them a specific name here. Anybody remember the name we gave them? Like, they are the component vectors, all right? Every vector that is at an angle has two components. Remember that a force that is pulling upwards to the right is pulling upwards and to the right simultaneously. We can draw that in as a horizontal component and a vertical component. A blue force that is pulling up to the left is pulling to the left and up simultaneously. Component vectors. Okay? Here's the deal with doing equilibrium in 2 dimensions. Right? Net force overall has to be 0. So we could do some vector addition and all kinds of craziness, but it's a little bit easier if we break it up into components, because if we have equilibrium overall, we have to have equilibrium on the x-axis, and we have to have equilibrium on the y-axis. It's much easier to handle each of those axes separately than to try to do them together. Okay? Good for starters? Technically, we would have equilibrium on the z-axis as well, but let's not get into that right now. Okay? All right. So let's talk about these 2 separate axes being in equilibrium. All right? Taking and splitting these forces up into components essentially takes that force away, right? And takes this force away and replaces them with the 2 components, right? They are acting simultaneously even though they are independent of one another. So essentially, we've now turned this problem into some angles, and now everything's on either the x-axis or the y-axis. Okay? Let's take a look at the x-axis first, because that one's a little easier to see. Right? how many forces are horizontal in this free body diagram now that we've gotten rid of the hypotenuse and just replaced it with the two sides? There are two horizontal forces. What do you see about those two horizontal forces? Well, let's go more. One is pointing this way and one is pointing that way, right? But if we have equilibrium, what has to be true about forces on the x-axis? They have to add up to 0. So what has to be true about this one and this one? One's got to be positive, one's got to be negative. Value-wise or magnitude-wise, Ben, how big do they have to be? Equal to each other, but in opposite directions. So when we add them together, we get 0. Okay? Good there? All right. Now, let's take the y-axis. How many forces are there on the y-axis in this picture? 3. All right? There is this one. There is this one. And there is, oh man, my settings got reset on here for a reason you don't need to know about. And something was messed up with my Google Chrome, and I had to use Google Chrome to log into Google, so they had to like reset my whole, yeah, like, and that one, right? That weight force, even though we didn't split it up into any components because it's already on the y-axis, is a force on the y-axis. Okay? Together, what do those three forces have to add up to? 0. Right? And now we're in a situation very similar to the bucket in case 2 that we just did, right? How many upward forces do we have in this picture? 2. How many downward forces do we have? 1. Upwards and downwards have to do what to each other? They have to cancel to make the net force on the y-axis 0. So what does each one of these y-axis components have to be? 9.07? Okay, that's fine. Oh. Sorry, Hannah, if you were watching this thing. So that means that this one has to be 9.05, and this one has to be 9.05. Okay? However, is that what this question asked us for? The question actually asked us for what? The hypotenuse, right? This is not the tension. That's a component of the tension. Specifically the vertical component of the tension. Okay? But we need to find the tension, right? Pink T. So, let's work backwards. We know some things about this triangle. We know this side and we know this angle. Which side do we know in relation to the angle that we know? We know this angle right here, right? So that means 9.05 is which side of the triangle? Opposite. And we're trying to find the what? Hypotenuse. So sine is the relationship between opposite and hypotenuse, right? So we know that sine of theta is equal to opposite over hypotenuse, right? But we're trying to find hypotenuse. So we rearrange this equation to look like this, right? Make sure you're in degrees.
Yeah, like on the homework, I was kind of, it doesn't work out really well on that.
Yeah. Our answer should be much larger than 9.05, right? Considering the kind of triangle we have set up. Anybody running through? 57.3? Anybody? Anybody? Well, I say that sounds better. Are you in radio today? Sine of 9.05 divided by sine of 3.5. Okay? 147.2, is that what it was? This stupid training is just gonna mess me up the whole day. I just know it. So. All right, good there? Okay. On the back page of your packets, you have 4 problems that.
Wait a minute.
What?
Please. I thought that, I was wondering, what if 48 plus 148 is not equal to 48?
No.
But then I know those are the
Just, yeah, and that's actually, Cindy, that's a good point. We should decide. So Cindy's question, or Cindy said 148 plus 148 doesn't equal 18. That's true.
yeah.
But 148 doesn't have to equal 18. The
That's
vertical
fine.
components have to equal 18. Right? Okay. Good there? All right. The last page of your packet has several two-dimensional equilibrium problems. Question number 3 and number 4, one that starts with this sign hanging here, and then number 4 is, I can't remember which one I gave you. Oh, the 2 water skiers, okay? Or the water skiers, or is it 2 boats pulling a water skier?
Yeah.
Okay. Very similar to the problems that we just did. The 2 at the top of the page are similar in that they are in equilibrium. And that means that our net force has to equal 0. But remember, we have to have equilibrium on the x-axis, and we also have have equilibrium on the y-axis as well, right? So keep that in mind as we're doing these. Okay? Your homework for the weekend, in addition to watching the friction video, is to complete the 4 problems that are on the back of that page. I will have answers to those problems posted on the calendar. So if you go to the calendar, that's not where I wanted. If you go to the calendar here, homework, it says, oh, there's actually a couple problems from the book. I put those up, I forgot. So, but I will put the answers to those 4 questions as well, so you can check and see out how you did. Okay? Good there? Sorry, everybody. That meeting is totally, like, messed me up, so. Bell's going to ring a little early here today because we have the Rose Arch and Homecoming Court Assembly later today, so we're dismissed.